Okay, welcome back. Next up, we are going to hear what is a Jellyfish open power provider by Igor.
Hello, everyone. First, thanks for coming here. I know there's RFID hacking in the other room, and I also wanted to go there. So thank you for being here. This is my first time at the BalCCon. Even though for the last couple of years I wanted to get here, but every year something happens. So yeah, I had really high expectations, but when I came here, this blew all expectations I have, and it's amazing conference, super friendly atmosphere, and amazing, beautiful people organizing this. So yeah, so from now on, expect to see me every year here. So and after this presentation, you'll see if that's good or bad. So so basically, I'm here to present a project I'm working on for the last year or so. It's called Jellyfish OPP, Jellyfish Open Power Profiler. And first maybe a few words about myself. So yeah, I'm basically software and hardware engineer. That's my profession, but I also do that for fun. I like hacking hardware, doing everything with that. I have also my job is doing custom hardware development for clients, and I'm one of the founders of the Radiona Makerspace from Zagreb. Yeah, I'm from Croatia, from Zagreb. I also wrote, I'm a wannabe musician, so each day now expect hard electro industrial EP coming out, but I'm mostly just collecting a bunch of gear and not playing it. So I'm just bragging about it. So yeah. I'm also wannabe yo-yo player. It's a really fun thing to do as a hobby. So Open Power Profiler. What is Power Profiler? What is the purpose of this device? I mean, this is not really a perfectly fitting theme into a hacking conference, but I think it should be because it has many uses. How I came to this idea, basically, since I'm developing hardware devices for clients, and for example, when you have some ultra low power devices, for example, smart sensors, IoT devices, they run on battery. Batteries need to last for months or years, and it's important to have a way to measure that consumption, to profile it, to be able to estimate how long the battery will last. And basically, and the thing with those IoT ultra low power devices is most of the time they're just sleeping and waiting for some event, and while they're sleeping, their consumption is under 1 microamp or something like that. And then they wake up and they try to do as quickly as possible to do their job, and maybe send the data through some wireless communication or something. And that part, they jump from that under a microamp of consumption, they jump to few dozen or few hundred of milliamps, which is 5 orders to magnitude, a lot of orders to magnitude higher consumption. And you cannot just take a multimeter, some instrument, connect it, because you cannot switch the range that fast. But if you want to estimate battery, you need to know each peak of the current consumption. You need to correlate it with the code to see I'm now turning on the LED or this GPIO, and this correlates with this peak. And if I disable that function, I will gain maybe a few more months of battery life or something like that. Power Profiler, it's not, I wanted also some other features. For example, when your device runs on battery, it has a charger, and you need a way to test that charger. I mean, you can put a battery inside and test if it charges the battery, but it's not reproducible. You want to see how it behaves when the battery is 10% and you just connect the charger, and will it crash, will something happen? So yeah, and I want something that can be used as general purpose power supply that can do many other things. We will see which ones in the next slides. So yeah, basically what I'm describing, like, we need a way to really fast, really precisely measure current consumption of a device. So really fast to catch all the peaks, and really precise to have, because if it's not precise, we can just get some relative view, but we cannot do anything with that. So, I mean, those devices that do that, they exist. They're called source measure units. And they're intended for laboratory use, for like testing the semiconductor devices or like doing this power profiling. But they're usually quite expensive. Like this kit is, I think, around 7K, but the price goes up really high and really fast. So the idea, and due to that, there are some like more specialized. This SMU unit can do a bunch of things, but for this exact problem I'm describing, there are some commercial devices which are lower cost, which do that. So basically, here are 3 of the commonly used devices for power profiling and measurement and stuff. The first one is OT ARC and OT ACE. Those are 2 devices. ARC is like a couple of years old. ACE is like from the last year. It can be used as like a power supply that can measure the current from nanoamperes to 5 amperes at 50 kilohertz sampling rate. It also has battery simulation profiling, which is like really interesting feature. But it's like the OTAs is 1,500 euros, and the software for it is like, I think it's 500 euros per year. It's a license, like subscription license. So it's it is affordable compared to the big tools, but it's not really for a sorry. It's not really affordable for a hobbyist or engineer on a budget. Like when you're starting with some projects, you don't have that budget. Other one is JouleScope. JouleScope does only the measurement, and it does that really great. That's a strong suit. It's also 900 euros, and the software is free. So it's widely used around the labs and people, engineers doing that sort of thing. And there is one really low power device with some limitations. It's called Nordic, from a company called Nordic, Power Profiler Kit 2, PPK2. It costs just around 90 euros. And it's like a small device. It's really amazing. It has limitation. It can only give like 0 to 5 volts, and it can measure up to 500 milliamps. But it can sample it at 100 kilohertz, which is great. And yeah, it's a great value. It has like software for it. It's not open, but it's free. And the schematics here is available, so people have been hacking it to add a few more measurement ranges. And it's really great. But in some projects, just those limits don't apply. So, for example, if you're powering the device from 4 AA batteries, it's 6 volts, and you cannot use this. Or if the current is a bit higher, so if you want to measure current in the other direction, it's not like easily done. So yeah, so basically what I wanted to do, I really like the PPK2, and I want to do something like that, but with slightly extended features, and to be fully open, both software and the hardware. So yeah, there's a thing called NLNet Foundation and the NGI Zero and Trust. It's an amazing thing. Like it's a it's a fund for supporting the projects which basically support projects who contribute to the open internet and open world, decentralized world, and fund them with some, like it's from 5 to 50,000 euros. And it's great because like they're supporting a bunch of open source and open hardware projects. Here's the whole list. And sorry. I don't usually talk this much, so. They're great because applying for a project is really simple. You just write a project page from like just a page or two. And they have like open calls each 2 or 3 months. I think in 1st October is the next deadline for project applications. So if anyone has any open source software or hardware projects, I really recommend like checking them out. So yeah, back to the device. What I actually want, all the features I want. So since I have a full liberty, full freedom to do whatever I want, so this is like my wish list of everything I would like to have. So basically, first thing is programmable power supply. 0 to 15 volts is enough for most of things. Up to 3 amps is also enough. I wanted to have to be able to act as an electronic load, so like for testing power supply, so it can sync, it can like dissipate some energy. Up to 10-15 watts is quite fine. And basically combination of those two things can be used to simulate the battery, both battery giving power and battery being charged. Because like battery is not just a regular power source. It has so-called internal resistance, which when the charge drops, it behaves a bit differently. And when you are developing a device that works on battery that needs to work for a long time, you want to like reproducible way to test how the device behaves when the battery is like almost dead and you try to send something. So you need to see what will happen and make sure the device works correctly. What else do I want? I want to be able to, like, the main feature is current measurement, but I want to be able to measure it in both directions, like both sourcing and sinking current. I want the wide bandwidth, so I can do the sampling really fast to get really precise measurements in time. And for that, we need to have really fast and automatic switching between those measurement ranges. And in a few slides, I'll explain why. Why do we need to switch between the ranges? It also needs to have so-called low burden voltage. It basically, that comes in the next slide, but basically, its ability not to affect the device being measured. So we want to measure the device as is, not to add some additional like error, noise, or similar. So now, like, nice to have things. I want it to be able to be powered from like many things. USB power delivery is really nice because you can use like power banks or wall chargers, which can give like up to 60 or 100 watts depending on the version. We can power it just like basically from wall adapter or something. It's controlled from the host, either computer or smartphone, or maybe to have some web app for controlling it, or the idea is also to be able to integrate it into EZ Studio, which is like amazing open source application for basically for controlling tested measurement equipment, but also for doing like full program logic, testing logic, and a bunch of other things. You should check it out. It's a really amazing tool. Optional feature is to have it isolated from the host device, from the computer, because we don't want to like add noise from our computer to the measurement circuitry. It should have nice onboard UI, because sometimes you want to use it without the computer or smartphone, just to use it as some power supply or to check something, to just turn it on and use the display on the device to do that. And let's add another small power supply for powering some, if we need something else. Let's add digital input-output so we can like correlate power consumption with some, for example, serial output or some pin toggling or something like that. So it's a bunch of things I wanted to add. So I went slightly overboard with it. But yeah, since I have full freedom, why not? So let's do it. We'll see later was the result of that. So yeah, and this is how the device looks. I have it here. It's like it has interface design, so it can be used both like this and like this. And it's still development, but if we power it, it has some nice shiny blinking lights. I added a transparent screen, so basically if you want to check it out, you can take it so you don't touch the components actually. So here it is, you can check it out. And why it's called Jellyfish OPP? Because like I wanted some to be named to be based on some animal because yeah, that's nice. I can have a nice logo because of that. And I was googling like what's the like efficient animal stuff, and some random website said like the jellyfish are most efficient animals. So I don't know if it's that true or not, but I really liked it because jellyfish are cool, and yeah, so it became Jellyfish OPP. So how is hardware design? What's the process of designing a new hardware device? Basically, we start with specification, which is what almost like list of features which we want to have, but in a bit more details. Based on that specification, we draw a schematic of the device, like defining each component, everything. Then we need to draw a PCB, like the board containing all the components. And then either ask some fabrication house to produce everything, or like order PCBs and you solder everything. Then you start writing firmware, testing it, and you'll see what you screwed up, and then go back to the schematic, fix it, repeat everything again, and then find out what next you screwed up. And after a few of those cycles, you have like mostly working device. Or number of cycles depends on the like complexity of the device. With some simple devices, it's just like one cycle, but yeah, sometimes you need more revisions, especially for more complex devices. Yeah, I'm currently in this firmware plus testing phase. I just got the first revision of the device like a couple of weeks ago, so I still haven't tested a bunch of things. So yeah, let's get back the function to like how do you actually measure current? This is like, it has some equations, but it's really easy. So there are like direct, indirect ways to measure current, because like when the current goes through a wire, it creates a magnetic field around it. We can measure that magnetic field, but it's harder. It's like it doesn't have that precision, and it has its own issues. But there's a much simpler way, because like we all know, or maybe most of us know, the thing called Ohm's law, which states that like when the current is flowing through something, through some resistance, it creates some voltage drop on it. So basically, we can use that to indirectly measure the current. So put a resistor in line with the device. Because they're in series, connected in series, the same current will flow through both. And we just measure the voltage, and the voltage is easy to measure. So we measure the voltage across that resistor. And we know the value of the resistor, and we measure the voltage, and we can calculate what's the current flowing through it. But because like that current, that voltage depends on the current flowing through it, and we have like a fixed voltage at the beginning. So that fixed voltage is like distributed, part on this resistor, part on this device we're testing. And since the like voltage drop on the resistor depends on the current, if we put the resistor too high, then when our device pulls a higher current, the voltage drop on this resistor will increase, and our device will get lower voltage. So basically, it pulls the current, and the voltage drops. So that's not good. It's affecting its state. So basically, that's what I mentioned. Like we want to have low burden voltage. The burden voltage is the voltage on this. So we wanted to make it so the voltage drop on this measurement resistor is minimal, like just we need to specify what the minimal means, but like few dozen millivolts or something like that. so it doesn't affect the device we're testing. But if you want to measure like a high range of currents, like I said, I want from from microamps to few amps, like that's really huge. That's number of orders of magnitude. We cannot use just one fixed resistor. So what do? Yeah, put few of them and like select which resistor we're going to use. So basically just few resistors, and depending on the current measurement we want to use, just switch that one we need. And if you want to do that, if you want to do like a really fast measurement, we need a way to automatically switch these switches to select the most appropriate range for that current. It needs to be done fast and like without affecting the device. So basically, that's the heart of this device. And I haven't actually tested how it works, and will my implementation be good enough, or I will need to do another revision? But yeah, that's the basis of it. So I started drawing us, like we knew from the cycle of development, we have specifications. Now it's time to draw the schematic, and I started drawing a schematic, and it took some time. While I incorporated every possible feature I like dumped in that specification list. And yeah, I tweeted this in April. So like what started as just a slightly better Nordic PPK2 ended up as like 22 pages of schematics, like, and it like grew a bit out of control. But yeah, let's start with it, and afterwards, when we have something, we can confer the functionality. Like we can then optimize and remove parts, and like it's easy to remove parts. So yeah, about the architecture of the device, like what do we want to have, how it's built, like what are the components on it. We need a flexible input power so we can handle like multiple input sources. To handle all of these things, components on the board, we need multiple power supplies. Like when I power this on, all of these LEDs are basically just indicators of power supplies that are working. So we have like, due to the number of functionalities, we have like plus 24, minus 5, plus 5.5, plus 5.0, which is like precise analog, plus 8, minus 8. We have a huge number of different power supplies to like cover everything we need. So yeah, we need some circuit to do, those measurement resistors are called shunts. So we need a way to do the switching between different measurement resistors. And we need a way to measure it. The measurement is done via analog to digital converter, which needs to run fast. So I said like 3 megasamples per second. It doesn't have to be that high, but like let's have the possibility. And since like we have some microcontroller, which should handle the user interface and the USB communication, I thought like why not add another FPGA chip on the board, which should be like which should handle just the sampling, so it does all the sampling and catching values, and the microcontroller can just do the like sending those data, because might be easier. We'll see. So yeah, and since it's basically a power supply, we need a way to finally regulate the voltage and the voltage which we can both send out and which we can send, and the current which we can sink. So basically there are two types of power supplies. There are so-called switching power supplies, and which are quite efficient, and they're used in most devices. And they work by like really quickly switching some components to get higher or lower voltage on the output. Like they are switching from like few hundred kilohertz to few megahertz. But the issue is like that switching can create some noise which can go to output and if we want to do some precise measurements, we really don't want that noise. And there are so-called linear power supplies, which are smooth, easy, but they work in a way that if we have some input 20 volts and we want to get 5 volts at the output, it basically just burns every extra voltage. Like you have 5 volts at the output and we have like a difference of 15 volts, which we need to burn somehow. And basically dissipates to heat, so it's really not efficient. So the way these things are done, if we want to make that linear stage more efficient, we need to minimize the difference between the input and the output. So the smallest possible energy is dissipated into heat. So we use the switching pre-regulator, which creates voltage just a bit higher than we need, and then a linear stage, which smooths it out, gives us nice control and everything. Actually, that linear output stage, which can be used to both source and sink current, is very similar to audio amplifier, Class AB amplifier. So it's a very known circuit from ages ago. And this is some sort of block diagram. I will just switch to schematic. You don't need to understand any of this, just to show it, because there's a bunch of it. So all of these blocks I mentioned are here. So we have an input block, which is input connectors and everything that goes to power supply. Here's the microcontroller, which controls everything. Here's the FPGA, which controls here's the FPGA, which controls the analog to digital converters. They have some of their own amplifiers for signal conditioning and stuff like that. So on like this. So basically, because we are dissipating some energy into heat, we need to have some way to efficiently take away that heat. So basically, that output stage, which is heating up, and the heat can negatively affect the measurements because it changes characteristics of the components. So I decided to put those power components on the back side and put the heat sinks, which is connected to some connectors. This is the output stage and these connectors. So we have also the front plate is also, I made it as a PCB because it's easier to just draw it and get the nice results. So it's somewhere also here. And yeah, so what I want to say? Yeah, and we have some relays. This relay is for galvanic isolation. This relay is to be able to we can use it as a power supply and to power something and measure that, but we can also use it just for measurement. So the relay can switch to, so we can get external input and just do the measurements, like the Joule scope device I mentioned previously. So, and after I drew schematic, drew this PCB, I ended up with this. So we have 760, I think it's 780 components in total, all of the components, from which 120 different components. That's not good because when you're ordering a device to be produced, the machines that do the assembly have a limited number of spaces for different components. So your goal is to minimize the number of components. I started with around 160 different components, but I managed to drop the number by using the same component at multiple places by doing the weird combinations to just reduce. And this could probably, I think I also lowered it now to I think 100 different components. This can be reduced, but this is the first revision, so it's fine. But the thing is, due to the number of components, and the number is high because of all the functionalities, the bill of material, the cost of all components together, is quite high. It's around 300 euros for one device. So yeah, like if you want to produce it, it's not really affordable. I mean, it's similar to other devices, and that's the reason why they're expensive, because the components are costly. But what's the next one? Yeah, but we can do some optimizations, because this is like a really high performance thing. Not everyone needs that. So the main component cost is in analog to digital converters. Like we have 2 of them, each one is 25 euros, and they have their amplifiers, which are expensive because they are precise analog things. So I also added, in this revision, I added some circuitry to be able to test. I mean, we have 2 ADCs, like as a baseline to see if it works. But I also added circuitry to easily test if I can use only one, but switch the inputs when needed, so that will cut the cost for like 20, 30 euros or something like that. So I have some ideas for these optimizations, but for the baseline we need to see what do we have. So this, as I mentioned, I got the device like a couple of weeks ago. It still didn't manage to test everything. But what I tested is the power supplies, the input power delivery. So if you connect it to the charger which supports it, or USB port which supports it, it like negotiates that it gives it 20 volts up to 3 amps, so it can pull 60 watts from the supply. The flashing programming of the microcontroller works. The programming of the FPGA also works. The blinking LEDs, the blinky LED. You'll see in here, this one is actually controlled from the FPGA, and this one is controlled from the MCU. This was just to test if it will work. Yeah, and the communication interface, UART and USB work. And yeah, I was thinking about, I'm currently writing like the drivers for each block of the device. I was thinking about going with, there's a thing called Zephyr Real-Time OS, which is now becoming like an industry standard, and many companies in that area, like, it's really popular and the way to go. But it's really interesting project, and it's like development model is similar to Linux kernel, and it's using the same like configuration tools and compiling tools. But due to that architecture, like it's easy to use for existing board, but if you are using it for a new board, you need to like define the device trees for each part, and it's like really complex to get to test it. So I managed to like write the blocks, write the definition for some parts, but I think I'll stay with like the bare metal, or using ST Microelectronics toolchain and their hardware abstraction layer to like do the initial testing, and then I can do anything else later. So also, while testing it, these things worked. I haven't found any like bigger issues, but I found few smaller issues. Like I have like 3 components which I turned in a different way, so I did some bodge hack here. You can see it where I like had to remove components, put some small wires and stuff like that. But currently everything seems to be going okay, so we'll see when I come to the rest of the circuitry. So yeah, the future is I need to verify the functionality. And as I mentioned, like this high performance device, not everyone needs it, and it's really costly. So the idea is, after I verify everything works and confirm everything's okay, the idea is to, for example, split it into few modules. For example, not everyone needs like 2 16-bit ADCs running at 3 megasamples per second. So that part can be on a like module board. So you can just remove it and just that part is like maybe 100 euros. You can remove it and put much simpler part, which is like good enough for 90% of use cases. Also, not everyone maybe needs like 2 power delivery inputs with the galvanic isolation and similar stuff. So that can be also on a module. So we have a base board and like few modules, so you can choose like mix and match to get exactly what you need and want. So, did I have to say anything else? So yeah, this is basically it. Just like this QR code leads to this website. It's my website. This is like the starting page for this project. On this website, I have like the summary and the links to all the part. I like each milestep. I did a detailed write-up. So, for example, here's the schematic, and now I like explained each part, what it does, and for the case, I like did it in a combination of KiCad, where I'm drawing the electronic parts, and the FreeCAD, which is used for 3D modeling. So, like started the case, designed like how everything assembles and stuff like that, and like PCB. And as I'm testing in a couple of weeks, I'll probably write another article, like summarizing the current state. And yeah, so basically this QR code leads to that page. And you can find at this first link, you can find this presentation if you want. The source code for both the hardware and software, and at some point FPGA, will be at GitLab. This is my contact and my Twitter handle, and yeah, that's it. Thank you very much. If you have any questions, please don't be scared to ask. So, yeah, thank you. Yeah, question.
So, thanks for that really interesting project and useful one.
Yeah.
Two questions about it. Number one, are you intending to sell it as kind of a developer product, so without certification and whatnot, but as a ready-made product?
I don't know yet. The current plan is to like finish it, to have like fully specified and working device with the hardware. I probably won't produce it myself, but I'm thinking about looking for some like open source hardware, like either shop or distributor or something, to do it in cooperation. So yeah, I mostly do just the design, don't do the production, but like I want to find someone like to cooperate with on that. So.
Okay, very good. And second point, now it's designed as a pure standalone product, which has its advantages in any case.
Yeah.
But did you ever think about taking, for example, the EZ Benchbox as a carrier frame? And
sorry?
From EZ, the EZ Studio, in the end, they also have their
the
rack benchbox.
I have it, yeah. So
as a plug-in module, so to say.
Yeah, I was thinking about that, but they also have, like the author of that power supply had some, started working on a module which could do power profiling, but never seems to finish it, and it's a bit simpler architecture than this. Mm-hmm. So yeah, maybe at some point I will also make a plugin module for that one. So yeah.
Okay, thanks.
Any more? Yeah. There's a question there.
Hi. I would like to ask about switching time between...
Sorry, can you just speak a bit louder?
Hello? Is it talking now? Okay. I would like to ask you about switching time between the shunts, actually. Do you have overlapping, actually, that two shunts are active in one short time, or you have interrupt, power interrupt, actually?
So yeah, that part I just tested in a simulation and haven't verified yet. I basically when I will switch there, I will do the overlapping, because not to create yeah. But also I haven't mentioned I have two shunts in series. I have one, the high current one, which is always active, and after it comes this switching part. So basically I can infer based on those two, I can first see if the current is rising or falling, and based on that, do the switching before it comes, before it's too late. And the switching, switching can be really fast, but the settling time after switching is about 1 microsecond, 1.5 microseconds. So, yeah, and that's the limit for like bandwidth and other things. So yeah, I forgot to mention. A lot of people. I had this device on this table outside, and a lot of people asked if it could be used for power glitching. Also because it was my alias at first, but then I gave the same name to my like company business entity, Hyperglitch, and because of that, people ask if it can be used for like power analysis, sidechain analysis, and glitching. And yeah, the answer is it depends. It's not that fast enough. For example, like the Chip Whisperer can do that at really high rate, but it doesn't have precision, because for that use case you don't really need precision. You just need some shape which you can trigger on. But basically, yes, it can be used because it has like programmable inputs and outputs, and you are able to basically trigger something based on the shape of the power usage and like detect some known patterns and stuff like that. So yeah. So yeah, if there are no more questions, thank you all for coming here. And yeah, if anyone wants to ask something, I'll be here for the rest of the day. So thanks.